Okay, this module is entitled the Directional Derivative. And what we're going to do here is we're going to kind of extend the use or understanding of the gradient of a scalar function and talk about the rate at which it varies along any given direction, number one. That is the directional derivative. Then the second thing we're going to sort of introduce or maybe underscore, in a sense it's clear, but we're going to make it more clear, is the interpretation of the gradient itself as indicating the direction of the steepest descent and steepest ascent up or down the function. Okay, so this is a very short module. We're not going to do any example, we're just going to introduce the concept here, and then later on in other notes we'll have specific examples of calculating directional derivatives, etc. Okay, so we had the gradient of our function f, okay, which is a scalar function to start, and we know that this is the partial of f with respect to x along the x direction plus the partial of f with respect to y along the y direction, along the j unit vector, and the partial with respect to z, k. Okay, so that gives us this vector valued function in general. Okay? If we wanted to know what the variation is along x, I mean, obviously it's just this, but the formal way to say that, to ask the question of, well, how does this vector field vary along a specific direction, in this case, the x direction, which is communicated by the unit vector I, we say, okay, well, what's the dot product of the gradient and the direction that we're interested in? Okay, so this is the gradient of f, it's a vector function. We're gonna dot it onto this vector, okay? And that tells us the projection or the amount of variation we have along this specific direction. Now clearly it's obvious what this is gonna be. Let's just remind ourselves for a moment of how that dot product works. Right? We had this certainly in first year and before. Dot onto I. You dot into every component, and so you have partial f x I dot I, and then plus partial f partial y j dot I, partial f partial z k dot I. Now I, j, and k are orthogonal, so this dot product and that dot product are 0. The only thing that's not 0 is I dotted onto I, which equals 1. So this whole thing just equals di f di x, which we knew. We knew that the gradient of f is a vector function, and the x component of that vector function is the variation of f along the I direction. Okay, so we knew all that. But the reason we say that, and we go through this little process here, is to allow us to make this generalization. So if instead of this, if we wanted to know, if we want to know the variation of f along some, sorry, not just f, the gradient of f, variation of gradient f along some arbitrary, here I'm trying to write u hat, okay, some arbitrary direction. So how would you find that? Well, it's kind of obvious now. You would say, and we give this kind of cumbersome notation, the directional derivative of f along a unit vector u is equal to the gradient of f dotted on to that unit vector. That's all there is. So if someone said, if we had a question, say, here's f, find the directional derivative of f with respect to a vector that's at 45 degrees between the I and j axes. You'd create a unit vector that describes direction 45 along the I and j. So it would have 1 over root 2 I plus 1 over root 2 j would be that unit vector. And then you would calculate the gradient of f as a vector, and then you would calculate the dot product of that function with that unit vector. And that would give you the rate of change of f along that direction. Okay, that is the directional derivative. So this thing here we call the directional derivative. In my experience, we don't use this word very often. We don't say directional derivative. We just say it a little bit longer. We just say, what's the variation of f along this vector? And we know that, okay, calculate the gradient and then calculate the projection, the dot product of that gradient calculation onto this unit vector, and that's the rate of change of f along that direction. We don't often use this directional derivative word. It's worthwhile giving it that name, I guess, but we really almost only use it in this course, in this section. After that, we just talk about component of the gradient, right? Okay, so that's directional derivative. And it comes directly from the concept of the calculation of the gradient of f. So now we can ask the inverse question, and that is, okay, so if we can say, well, how much does f vary along that direction? We could ask a related question, which is, well, what direction does f vary fastest along? What is the direction of steepest descent or steepest ascent? So if we're thinking about f as the altitude over Mount Fuji, right, and x and y is the plane here, and we're standing on a point at some xy, we can say, well, what direction do I have to go in which the altitude varies most quickly? What's the steepest direction down, steepest direction up? And you can tell it's certainly not parallel to the level curve. The tangent to the level curve, I should say, is the direction along which you don't change f, right? It's a constant. So clearly you know this, right? It's downhill or it's uphill. It's not along the hill. We can ask that question at this point, and what we're going to find is it's just the gradient itself. Okay. But here, let's just do that for a minute. It's a simple point. Okay, so I'm going to call this steepest descent or ascent. They're actually completely related. The direction that is most rapidly going down is exactly the opposite of the direction most rapidly going up. Okay. So let's just say we have this directional derivative, right, of f, okay, which is the gradient of f dotted onto u. Okay, let's just ask, well, how big is this thing? So the magnitude of that directional derivative, right, would be the magnitude of the dot of f dotted onto u, okay, which is the magnitude of the gradient times the magnitude of the unit vector times the cos of the angle between them. Okay, so this phi is the angle between the gradient of f and this particular to be determined direction. Okay. Now, this angle has to be between -1 and 1. So -1 less than or equal to cos phi less than or equal to +1. Right? The angle between them can only be between 0 and pi. Right? And so the maximum value this could have is 1, the minimum value could have is -1. But it can't ever have a magnitude of greater than 1. So that means that the magnitude of the directional derivative is between the negative of the gradient, arbitrary directional derivative, and the positive of the gradient of f. Okay? So that means that the gradient of f is not just the variation of f as a vector field. The gradient of f at some point is the direction of greatest change in f. Okay? So if f is the altitude field of a mountain over the xy plane, the gradient of that altitude function gives us a vector. If you evaluate it at a point, gives us the direction at which we are most rapidly increasing, and the negative of that is the direction we're most rapidly decreasing. Okay? So the gradient isn't just a field describing the variation of f, it also points to, when evaluated at a point, it points along the direction of steepest descent or change. Okay? As that, it's a very powerful thing because lots of things we want to do in physics relate to that. Place a ball on the hill, what directions is it going to go along if it has zero initial velocity? It's going to move along the direction of steepest descent, and that you could calculate that from the gradient itself. Okay, so we're going to use this, we're almost just going to take this for granted as we go forward, that the gradient is always the direction along which variation is most rapid. Okay, we'll see this in a couple simple examples, but really we're just going to use this as we go forward. Okay, and that's the end of the directional derivative module.